Hey, everybody. I am very excited for this Friday chat today with Infinera, a company that's really revolutionizing the optical communication space. Really intriguing technology for a geek like myself. Robert, how are you?
Doing great. Yeah, thanks for having me on. As you said, a lot of
Well, happy.
interesting and exciting things going on in the industry right now. So it should be a good conversation.
Well, I'm excited to have it. Before we jump in with lots of questions, maybe introduce yourself, your mission personally, and a little bit about the team.
Yeah, great. So I am Rob Shore. I work for Infinera. I run the marketing organization. I have been in telecommunications networking for, I'm embarrassed to even say because it dates me, but just over 30 years, about 32 years. And what telecom in general does, and Infinera specifically, is really try to connect people, right? So to enable people to
Mm.
connect to applications, to the internet, to the web, to data centers, to applications, and just enable people to communicate and live better lives. And what Infinera specifically does, not sure if everybody's fully aware of the fact that almost all communications on Earth are transmitted over fiber optic cable. So little glass cables that are about the width of a human hair, and then lasers are used to transmit information back and forth, and everything we do transmits information. And what we do at Infinera is we build the lasers. We build the lasers that help transmit that information over that fiber cable, whether it's just down the street or even under the ocean, right? Lots of submarine cables, which is how information gets from one continent to the next. So we focused on continuing to innovate new technologies to enable us to transmit more information over greater distances and faster, giving us fun things like this video conference, for example, but streaming video and music and all that kind of stuff. And increasingly, as we get into artificial intelligence, it's driving the need for bandwidth and connectivity solutions even greater. So, yeah, all really interesting stuff. A good mixture of physics and chemistry.
I love it. And given our desire, our need for almost infinite bandwidth and connectivity and storage, it's you guys are in a very important position. And talk about your position in the industry as an optical semiconductor supplier. But you have a unique approach from a tech stack perspective. Tell us about your strategy and kind of solution set.
Yeah, it's interesting. I mean, what a lot of people don't realize necessarily is there's lots of different types of semiconductors. Most people think of
Mm,
semiconductors as silicon, right? Memory and
mm.
processors. But the reality is there's a whole host of different types of semiconductors, and they do all kinds of different things. For example, even this LCD screen that I'm looking at right now is based on a semiconductor material.
Mm.
We build semiconductors, are called compound semiconductors because they integrate two different elements together. And we built semiconductors based on indium and phosphorus called indium phosphide. Those are really, it's a really efficient vehicle for transmitting light. So particularly at the appropriate frequencies to get it to propagate across a fiber effectively. And so what we've done is because pretty much all these high powered lasers that transmit information, they all need indium phosphide. So it's a base component for virtually every optical transmission solution in the world. We leaned into that and we built our own fab. So we run our own fab right there in
Mm.
California, and it's an indium phosphide based fab. But these optical lasers, or we call them optical engines, because there's a lot of different components necessary to transmit the light, control the frequency. Most people, it's 50, 60 different individual components that they glue together to produce these lasers. What we did is we leaned into the fact that you need indium phosphide to make it happen. And we built all of those components, or most of those components, onto a single individual chip based on indium phosphide that we call a photonic integrated circuit. And we really, like I said, leaned into putting as much as you possibly can onto that one chip. So what takes many other people 20, 30 chips that have to be glued together, we can produce in a
Wow.
single chip that's about an eighth the size of a dime. So very, very, very tiny. And then again, it enables us to be more efficient. A, because we've integrated it, and B, because we own our own technology and enables us to innovate more effectively. So we can really push the boundaries of what physics enables, because as you said, there's never a slowdown in the appetite for more bandwidth. So we need to continue to innovate. And about every 2 or 3 years, you come up with a new generation of these engines that produce information or transmit information faster and faster. Our latest generation off of a single chip can transmit 1.2 terabits worth of information per second. And the way we design it is that we can actually transmit about 60 of those signals down a single fiber. which can get you a total of about 100 terabits of information on a single pair of fiber optic cable. So yeah, quite a bit of data.
That is phenomenal. Literally rocket science,
Yeah, exactly.
what you guys are doing. And the bottom line is it's, massive improvements to your OEM or clients' network performance and efficiency. Maybe give us some examples of the bottom line impact, whether it's a government or a carrier, even, large global enterprise, maybe.
Yeah, it's interesting too because kind of like the mail system, like you think about the, mailing a letter, most people really only interface with the very, very front end of that process, the mail carrier, the local post office. But the reality is there's a huge amount of infrastructure necessary to actually get your letter from one place to the next. And the internet and connectivity is the same way. Most people see the entire internet as their local service provider, Comcast, Verizon,
Mm.
AT&T, whether cable. And that's just that. We call that the last mile. But there's a whole network that operates behind there. And that's what we really focus on is, again, if you use the analogy of the mail system, we don't build the little sedans that come around, little mail trucks that pick up your mail. But once it gets to that post office, to go from one post office to the next or across the city, there's bigger vans, trucks, boats,
Hmm.
airplanes. Those are the things that we build. So we build really these high-powered engines that help transmit large amounts of information from place to place. And what's interesting too is the amount of there's what's called north-south traffic and east-west traffic. North-south is U
Mm.
to that's only about 20% of the traffic is north-south, and it's skewing even more heavily as we go. Most traffic is east-west, from data center to data center, from office to office, and it's just huge volumes of traffic. The traffic in the network is growing, and it's pretty consistently for the last 20 years at about 30 to 35% a year. That means every roughly 2.5 years, the amount of information that needs to be transported doubles. It doubles every roughly 2.5 years. It's a really, really challenging problem for network operators. And one area we're seeing a huge amount of growth is data center to data center traffic, right? You can imagine, when Netflix wants to distribute a bunch of movies, they've got a centralized location. They've got to send those everywhere, right? Each one of the localized data centers needs that same information. You travel with, use Facebook. When I travel from here to San Francisco, Facebook will replicate all of my data to a data center local to, I should say, Meta will
Mm.
replicate all my information to a local data center. So there's this huge amount of east-west traffic. And with artificial intelligence now, particularly this generative AI like ChatGPT, the amount of processing capacity and connectivity capacity is about 20 times what a traditional application will require. Now, right now, that AI stuff is mostly inside an individual data center. So they have these
Mm.
things called AI clusters, which are these racks of servers, and it's all. But now, as we're getting more and more sophisticated AI and a broader adoption of these capabilities and technologies, they're needing to grow this out. And one of the biggest challenges that they face, sorry to ramble on here a little bit, but it's
Please.
power and cooling. Even within a single physical building in a data center, the amount of power and cooling that a AI cluster requires is immense. And they actually have to, inside the data center, separate these clusters out, right? They have to put space between them so they can have the power density that can power these racks and cool them. So even inside a data center, there's multiple hundreds of meters of connectivity required between one AI cluster and the next. In some cases, they go to a campus style implementation where there's like 7, 8, 9, 10 buildings on a single campus
Wow.
to keep things separate. And now they're getting to a problem where cities can't even provide enough power for some
Mm.
data centers. So they're having to build these remote data centers, these very distributed implementations where there's maybe 100 kilometers between data centers, so they can feed off of different power grids. I remember reading something about Microsoft wanting to build a huge data center somewhere on the East Coast, and the city's like, this is 3 times the amount of power the entire
Oh,
city
jeez.
requires just to power this one data center. So this is where we can help, right? Because we can provide the connectivity solutions either between inside the data center, high capacity between these AI clusters over a couple hundred meters, and also a couple hundred kilometers to go between these individual distributed data centers to try to help keep the processing speeds up between them. So yeah, a lot of really
Wow.
interesting things going on.
That is huge. So exciting, and not just on land, above land at data centers, but you play an increasing role within advanced submarine networks. Most people don't realize the world's connected by tubes under the sea. It's
Yep.
simply, I love the anecdotes and stories around the role you play there. Maybe describe exactly what you're doing with your customers.
Yeah, it's as you say, it's a unique capability of being able to transmit information under the sea. When you're on land, you can always stop at various places to regenerate the signal.
Mm,
You can't do that in the subsea. There is no power stations. There's no way to power that. All of the cables are remotely powered. So there's these huge, massive cables that have the fiber in them, but they're actually clad all the way around by copper to feed power down the cable. So there's a very finite amount of power. So you have to build these lasers optimized for these types of applications, and how the way you manage the power and balance all these things. Some interesting statistics, by the way, on fiber optic cable that kind of blow your mind when you start looking at the numbers. But humans have been deploying fiber cable for telecommunications networks for about 50 years now, maybe 55
no
years.
kidding. God, now I really feel old.
I know exactly. Yes, it was in the really kind of the mid 80s when it really started taking off, or early 80s. But since that time, humans have deployed enough fiber optic cable to completely encircle the Earth 200,000 times.
Wow.
So that's a lot. Earth is about 40,000 kilometers in circumference. So and they expect that amount of cable to double in the next 10 years. So just a huge amount of cable. The same thing is true with submarine cables, right? Particularly because historically these submarine cables were built by consortiums of traditional service providers like Verizon and AT&T and that type. What we're seeing increasingly is the data center operators or hyperscalers like Amazon, Meta, Google, because so much of the capacity carried on these cables is their services. They started investing in their own submarine cables, and we're expecting the amount of submarine cables in the next 10 years or so to double. And there's a couple hundred submarine cables, and we're going to see a
Wow.
huge increase in the number of submarine cables, largely to interconnect these data centers. So yeah, it's just the amount of information that needs to be transmitted is just mind-boggling. And just to give people another couple other key perspectives on this, if you're familiar with the satellite system, right, Elon Musk's Starlink system,
Mm,
that'll have 30 some odd thousand satellites or something like that. The total capacity of that entire network is about 90 terabits per
mm.
second, which seems like a lot. But as I mentioned before, that's the capacity of a single fiber optic cable. A single fiber optic
Oh,
cable can
wow.
carry about 100 terabits. So the Starlink system is a phenomenal system, particularly for really reaching remote areas and providing internet access for places that are difficult to put physical fiber. So it's an extremely valuable solution, no question about it. But it just isn't nearly enough to carry the kind of capacity we need for the bandwidths and workloads that we're talking about now. So yeah, fiber will continue to play an increasingly valuable role. There just is no better way to transmit information than fiber optic cable, and we need to continue to innovate new ways to do that to keep up with the bandwidth demands. And artificial intelligence and augmented reality and self-driving cars, it's only going to continue to make the situation substantially worse as we go forward.
Wow. So, given all that insatiable demand for data and bandwidth, I mean, give us a peek. How do you keep ahead of the curve? How do you keep innovating in terms of capacity and, of course, cost effectiveness at the silicon, at hardware, other levels to
Indium
ensure
phosphide.
you're ahead of the curve?
Yeah, it's a great question. It's there's been a couple of key innovations over the last handful of years that have made a really big difference. One thing is we use something called dense wave division multiplexing, which is a complicated way of saying our lasers transmit light in individual colors, so the very
Mm,
specific color or frequency. This enables us to put multiple optical signals on a single fiber cable. So you literally use a crystal to break the signals out, and like a prism, so that I can break the signals out. And I can then extract each individual optical signal separately. But dense wave division multiplexing was a big part of how we could add more capacity per fiber. And then about 15 years ago, we came up with a new technology, we as an industry, called coherent optical transmission technology. And what this did is its historical signals use amplitude, the power modulation. So high power, low power,
mm.
1010. With coherent, we actually use, for those who remember high school physics, light is both a particle and a wave. and we were using the waveform properties of optics to manipulate the signals. And so the benefit of that is power. As you transmit power over distance, the power goes down, right? Just think of a flashlight, it dims over time. So it's very difficult to transmit that over very long distances. When you use the waveform of the optical signal, that doesn't change over time. Even though the power goes down, the waveform stays the same way. So you can transmit that over much greater distances. On top of that, instead of just a 1 or a 0, we shift the waveform back and forth, and we can do this to granularities of 64 different shifts, so to speak. So we can transmit a lot more information over much greater distances. And then we just continually have been increasing the complexity of the way we transmit that optical signal. So that's been a big part of it. One thing that Infinera recently did is, you think of like your FM radio, there's a certain number of stations that you have on the FM radio. What we've been doing is trying to increase the number of stations, increase the range of frequencies that we can transmit information over. Again, to use another analogy of like a highway, we're trying to not only enable us to put more information in each lane, so build bigger and bigger cars so that each car can carry more information, but at the same time, we're expanding the highway so we can put more vehicles on the road. And obviously there's technology involved in that, and ensuring that I can have cars that can drive on that parts of the range. Like, think of your FM radio. You need to build a radio that can tune to a wider range of stations. And we need to do the same thing with optical technology, enable these cars to be tuned, these lasers to be tuned to a wider range, and then all the other ancillary aspects, right? Again, like on a road, you can't just build a wider road. You need to build roundabouts and intersections and all kinds of other things that can now handle this wider road and larger volume of traffic. So all of these are ways to do it. Now, we are coming to a head here where there's only a certain amount of information you can put on an individual fiber. There's actually a gentleman by the name of Claude Shannon, who I believe in the 60s theorized.
Yes.
Yeah.
Shannon's Law. I have a double E, so I recall him now very well. But please, refresh our recollection.
Yeah. So he theorized the maximum limit of information you can put on a fiber in a given amount of spectrum. It wasn't even fiber related. It was really just in a given amount of frequency, how much information you can transmit. We're basically there as an industry, right? We are scratching the ceiling of that. So we are reaching the limit of how much information you can put on an individual fiber. And this is going to cause a big shift in the industry as well. We're going to have to start thinking of networks in more parallelism. So rather than looking at two locations connected by a single pair of fibers, we're going to have to build them as like a fiber. But we do this already, by the way. There's a bunch of fibers in this sheath, in this cable. But we're going to have to think of this as a collection of fibers connecting these locations, and build components that aren't focused on managing traffic on an individual fiber, but can manage multiple fibers at the same time. So it's looking at kind of multiple. It's almost like thinking of a highway system. Instead of just a highway with more lanes or bigger cars, we're going to stack the highways on top of each other and then try to manage them all as one. Now, this will take a fairly significant shift in the way we build technology and the way we build these networks. And that's probably maybe 5 to 7 years out that we're going to really have to start tackling that problem and addressing it, I think, in a more parallelized, is that a word? Parallelized way. Yeah. Some other things too to think about, but artificial intelligence is another thing we can really start taking better advantage of, because like think about trucks on the highway. Most of our trucks, as they're traveling down the highway, on average are only about 30% filled with information. Sometimes they're 100% filled. So again, we establish these paths because we want to be ready for the rush hour of traffic. But again, the rest of the time, like our highways, are empty, right? They're mostly very lightly utilized. So could we leverage artificial intelligence to better use traffic? Wouldn't it be great if you could reallocate lanes from a highway over there that you're not using to this where the rush hour traffic is, like during rush hour? So if I could rearrange the highway dynamically, which, by the way, the technology is capable of, we just don't have the tools to intelligently do that rerouting at the moment, dynamically and intelligently. So could we use artificial intelligence to enable us to leverage the resources we have more efficiently? And that's definitely a direction we're going to go. And it has to be done predictively. You can't wait for the requirement and then make the adjustment. By then it's too late. You're already going to see delays and packet loss. You need to predict where you're going to need it, rearrange ahead of time, and then when the traffic arrives, right, the resources are already available to handle the increased workloads. So
That's phenomenal. This is quite a master class. Thanks for that.
yeah.
Uh, so when it comes to things higher up the stack that you're involved with, new connectivity standards, open network movements, how do you play into those activities and make contributions to those kind of standards bodies? Maybe talk about the community that you're a key part of.
Yeah, it's just another really good point. It's a transition we've been seeing going on in the industry for probably about 15 years. But like most things, it starts with the trickle, and it takes a while for
Mhm.
the real flow to start going. But we call it open networking, and the idea is historically, when you build networks, first of all, each network was relatively insular. You've got the optical network, the
Mm.
packet network, and the applicant, and they were all very insular, and you had separate organizations that manage them. And there's really these relatively excuse me, solid walls between the organizations, but they didn't even really communicate that much. It's actually funny. If you see like router people, when you see them draw networks, there's just a bunch of routers and they just draw lines directly between the routers. When in reality, there's a whole optical network infrastructure in between, and they'll have signal paths that go from router 1 to 2 to 3 to 4 to 5. So if they want to get from 1 to 5, they have to go through all these other routers. And the reality is there's an optical highway right between 1 and 5, but the router people don't even see it. So
It's
they
the
would,
same in 5G. I mean, everyone assumes that it's just a connection of towers, and of course, backhaul between data centers and
yeah,
those radios is fundamental to those speeds that we want and need on our devices. So, but yeah, I
yeah.
digress as well. So
No,
go
no.
ahead.
It's. I mean, it's a great corollary there. But this is one of the things we've been focused on. How do we get these layers of the network to work better together so we're using resources more efficiently? Um, but now also what we're seeing is even within the optical network, they were very univendor, right? They were very monopolistic in terms of it'd be an entire one network would be one vendor and that would be it. And a lot of times all these components really worked closely together and synchronized to make them work right. Well, we've been working a lot on separating that stuff so that each individual function operates independently, the line system from the transponder. So network operators could pick and choose individual technologies independent of vendor. They can pick one vendor for the highway, then they can pick 3 different vendors worth of cars, 3 different laser vendors. And we've done a lot of work there, and I think that's gone pretty well. Part of making that happen is the technology itself needs to be able to interwork together seamlessly. The other part is it needs to be capable of being seamlessly managed. Um, we work on our own to make the technology work properly, but then we all get together to talk about how to manage these things. And this is where you talk about whether it's Optica or IEEE or Open Road and what are all these standards organizations that really focus on how do these devices communicate northbound so they all speak the same language to the management system. And again, it takes a long time to make this happen properly, not only for us to implement it on the platform, but for us to agree. There's 7 standards organizations, and which one are you going to go with, and what do you actually want these northbound interfaces to look like? But after about 15 years of working towards this, we've really pretty much gotten there now. So really, these standardized northbound interfaces and CMIS and those types of communications, we're really all pretty standardized now. So you can build ubiquitous management platforms that can manage things across the board. One other thing we're seeing is an integration of technology. So we used to have routers and transport platforms, right? The routers would emit gray optics, right? Just white light. And
Mm.
then the optical platform would convert that into these color DWDM signals, coherent signals for long distance transmission. And part of that was because the engines to do that, the lasers to do that, were relatively large and power hungry. So you want them on a separate platform. There are other reasons, but that's one of the reasons. As technology has evolved, we can build these lasers smaller and smaller and smaller. And we build them now into what pluggable form factors, about the size. I've got a Swiss Army knife here, but that's about how big these
Wow.
pluggable optics are. And you can now take those and put them, and they're the much lower power. So you can take those and plug them directly into the routers now. So there's this convergence of routing and
Oh.
optical onto
Uh-huh.
a single plane. And this is causing us also to rethink about the way we manage both the optical layer, but router layer, and the intersection between the two. And that's driving a lot of this coordination as well. And even more, right? You're seeing even people like NVIDIA right now. Most of NVIDIA connectivity that they build in their AI clusters is electrical, and that works really
Right.
well for very, very short distances. But as soon as you go from one cluster to the next, especially as you have to separate them in the data center due to power and heat, that requires optical connectivity. And so you're seeing not only a tight integration between routing and optical, but you will also see it between compute and optical as the amount of information that needs to go between these clusters continues to grow. It'll eclipse electrical's ability to handle it. And where even some of these lower speed optics, um, it's eclipsing their ability to handle. We can continue on the same trajectory right now for one more generation. We're going to the 800 gig generation of intra data center connectivity. So between one cluster and
Mm,
the next, it's about 800 gig. That's
mm,
this generation we're just seeing come out now. The 1.6 terabit generation, which is what's next, that'll probably require a new type of technology, which is what we, by the way, just announced. So we call it all our optical engines are called ICE, Infinite Capacity Engine. Right? You talked
mm.
about it. I smirked when you said an infinite capacity
Nice job on
requirement.
the marketing
I
side. Very,
know.
very nice acronym.
Um, uh, Mostly it was for inter-facility, between facilities is what we've been focused on. But as the requirements inside the data center start to grow, our technology, which is really optimized for ultra high speed transmission capabilities, it starts becoming more applicable even inside the data center. So we've just launched this new brand, a new line of chips that are really focused on 1.6 terabit and beyond of intra data center connectivity, super low power but super high performance, to go between clusters and around a campus data center, not within the cluster. Inside the cluster will still be electrical for quite some time now, I think. But between clusters, not only is optical today, but it's going to require a new type of technology to go past 800 gigabits per second.
Wow,
Yeah.
1.6 terabyte. That's extraordinary. So you have so many great customers and case studies. Care to call out any names or examples without, having to pick your favorite children kind of thing? But
Yeah,
yeah, maybe talk about a real world deployment.
yeah. I mean, first of all, for the intra data center stuff, that's new. So we just launched that. So we're looking at
Mm,
partnerships right now. The other thing too is, the hyperscale operators are always very sensitive about using their names for anything. So I'll probably try to stay away from mentioning any of them. But you can rest assured we're working with all of them. I mean, we'll talk to everybody, trying to make sure we're optimizing our solutions for whatever their needs are. Um, and it's been an interesting inversion of innovation in the industry, because for the 30 years I've been doing this, the people driving innovation were the traditional network operators, the Verizons and AT&Ts. They had the big pockets. They spent all the money, and hence we really tailored our solutions around their needs. And then the hyperscalers, we'd add in a few features that they wanted, but they would fundamentally largely use what the traditional network operators want. That has been changing. The hyperscalers, the data center operators, are really the ones that are being more progressive, embracing these new and more innovative solutions, and really driving the technology. So you're seeing a lot of these solutions now morphing into more optimized way around the way the data center operators build their solutions. And of course, in order to make that happen, we have to work very closely with them. So I don't think there's any outside of China that we don't work with on a very close basis. Again, I can't state who our actual customers of ours or not.
mm,
But from a network operator perspective, I mean, we just announced a big press release with Orange. We've got pretty much almost every
mm.
carrier in North America we do business with, and it's just interesting. I mean, while they all use the same fundamental technologies, the nature of the networks are very different. We have one customer, and we've got a press release coming out about this soon here, but most fiber optic transmissions use two fibers. One transmits this way, the other transmits that way. That's how you do the transmit and receive. Um,
Right.
but there's some people that have single fiber deployments. So it's literally just one fiber, and they have to transmit information in both directions down one fiber, can be quite challenging. Um, and we have technology, the way we build our lasers, we use something called subcarriers, but it enables you to use some subcarriers in one direction and some subcarriers in the next. So we can actually transmit in both directions down a single fiber with one laser. And that helps a lot of those types of operators. And also, for those who have fiber to the home, hopefully everybody knows what that is. So they call them passive optical networks. They're fiber all the way to your home. So it's not cable or DSL, but fiber to the home. Those are all single fiber infrastructures. So one of the things we've learned we could do with this unique technology we have is, to the home, you're looking at tens of gigs, right? That's what they do in these access networks to people's homes, is tens of gigs. That's fine for residential services, but it's not good for businesses. You can't leverage that infrastructure to offer anything other than, relatively basic business services. But using our technology, you can layer it on top of this single fiber infrastructure, and now offer 100 gig, 200 gig, 400 gig services to businesses, to what they call anchor tenants, like hospitals and financial institutions. So we've done a bunch of, I can't remember them off the top of my head, but there's a number of customers in Southeast Asia that are doing it, in Latin America that are doing it. And I think you're going to start seeing here very soon some North American companies that are also going to leverage their single fiber access infrastructures, like their fiber to the home infrastructures, to start using this technology to offer business services. So,
Wow, amazing. Well, that's quite a tour de force in the fiber optic space. So much I didn't know, had no idea around. And speaking of education and other things, you have the big OFC 24 event coming up in San Diego, the big optical networking event. You'll be there in force. Tell us about that event, what you're excited for. I even see you guys have a party on
we
the
do.
USS Midway, which that sounds like an absolute blast, literally.
Oh,
But
yeah.
what are you looking forward to in San Diego?
Yeah, just real quick on the party. I mean, this is an industry event, so there's, I believe, 15 sponsors of the event. We are one of them. Of course, we're spearheading the effort. But yeah, it's on the USS Midway, and we hired a band. The name of the band is called Hairball, and it's really fun. They're an 80s tribute band, but they have a number of different vocalists, and they dress up like the famous 80s characters. So Van Halen or Kiss or Journey, and so they dress up like them, and it's a big show, and it's all the biggest hits. So. And like you said, it's on the deck of an aircraft carrier, so it should be really, really fun. It is open, by the way. Anybody who's watching this, it's open to anybody with an OFC badge. So if you got the OFC badge, you can just go on. There's no entry fee. You don't need to reserve a spot. You don't need to buy tickets. There will be drinks and food served on the ship. So, okay. Anyway, that's the party. Should be super fun. Wednesday night at OFC. But yeah, no, I mean, OFC, there's a technical conference part of it, and then there's an exhibition part of it. The technical conference, really, a lot of people focus on future-looking technologies, and this is we're going to talk a lot there. We have 15 different speaking slots, a lot about evolutions in ROADM technology. There's a lot of really cool things that can happen there for those who are familiar with ROADMs. That switches light on the fiber, and then a lot on the actual laser technology itself. So where do we go from here? And we call it in the shadow of Shannon, right? So now that we've entered the Shannon limit era, where do we go from here? And then I can't remember, but what happens inside the data center? So there's a lot of innovation, very different types of optical connectivity solutions required inside a data center, as you might imagine, than one to transmit information across the ocean. So that's what happens in the technology in the technical conference. In the exhibition center, we really focus more on solutions that we have available today or in the very near future. So that's where we're going to be demonstrating our 1.2 terabit optical engine, right? That's capable of transmitting, 1.2 per signal, and then 100 terabits of information on individual fiber. It's where we're going to be highlighting our ROADM that has more lanes on the highway. We call it super C-band. So it's a wider range of frequencies to enable customers to transmit more information on each fiber. We'll be highlighting our little pluggable optical engines, so the ones that go directly into routers. One of the key things you have to show there is multi-vendor interoperability. So the ability to take our pluggable and put it into multiple different vendors. So we have 5 different vendors, routers in our booth, including, I think we announced a DZS, which we've done before. We're going to have Arista in there. We've got Juniper routers in the booth. So again, a whole host of different routers in the booth that we're going to be showing our pluggable works under. And then really interestingly, the next generation of pluggable, the current generation is 400 gigabits per second. The next generation is an 800 gig. So while the big engines are 1.2 terabits, the pluggables are 800 gig. And we're doing an augmented reality tour of our 800 gig pluggable. So it should be super fun. I mean, they're small devices and there's a ton of tiny components in there. So what we've done is you're going to put on your augmented reality goggles and again, augmented reality, not virtual reality. So you'll see everything around you. And then at the table that you'll be sitting at, our pluggable will rise out of the table and then grow to be about 6 feet big and then pop open. So you'll get to really examine all the individual components inside that. And there's a lot of unique things that we can do in design efficiency with our photonic integrated circuit. The fact we integrate all these functions onto a single indium phosphide based chip, and you can really zoom in on that. Because again, like I said, it's this little tiny thing, but we'll blow it up and you can actually see everything that's going on in there. And essentially what makes our design more efficient enables us to get better performance with lower power in a smaller package. So, and then we have some artificial intelligence demos too, but that's early stages yet.
Wow, it sounds like you'll be a kid in a candy store there,
I know
and
it's super fun.
it's very fun for technologists, CTOs, and beyond. Well, thanks so much for just sharing that vision and all the education, the mission. So exciting. We'll be watching your posts and tweets and blogs at OFC 24. And thanks everyone for watching. Reach out to Infinera with any questions or comments. Follow them on social. They're really informative content. And have a good weekend. Thanks, Robert.
Yeah, thanks a lot for having me. Having a great conversation.